We've set up a simple stretch test. The left face of this cube is moved leftward, or it would be if Newton's method managed to solve the nonlinear equations for the first frame. Next, we let the sim continue, whether Newton's method converges or not. If we decrease the time step, then Newton completes successfully. By recasting the system of equations as a minimization problem, our method is able to solve the system at the larger time step. In this example, two spheres collide with each other and the ground. In this visualization, each pixel corresponds to a different initial configuration of the mesh. The two 3x3 blocks are rotated and scaled according to the location of the pixel, which is shown as a large circle. The lighter the blue, the more iterations required. Red means the method didn't converge after 500 iterations. In this test, a cube is collapsed to a point and then allowed to expand. We run the same test again with a higher stiffness. The stiffness is increased again so that the cube expands in a single frame. In this visualization, each frame is an iteration of our method. The bar on the left shows the logarithm of the energy. Below, red CG indicates conjugate gradient finished early due to indefiniteness. Red LS indicates the line search chose a non-unit step length. This shows that both these techniques are often needed to ensure the energy decreases. In this test, we randomly arrange the vertices of a cube mesh and then allow it to return to its rest state. At this stiffness, the cube recovers its shape in a single frame. Here, we compare three different collision resolution techniques. Here we show how our line search routes around objects. Absent constraints, we would search along the red line for a sufficient decrease in energy. With constraints, we search along the blue curve. If the green steepest descent direction points into the object, we stick. Otherwise, we can separate. This example shows our constraint collisions in action. Here we show constraint collisions against cubes with sharp corners. Here we show our penalty self-collisions. Here we show our penalty self-collisions with cubes with sharp corners and varying stiffness. This example shows that our method can handle a large number of objects.